So far we have been revolving around the x-axis. We now want to revolve around the y-axis. So in this case our surface area is going to be the integral of 2 pi x ds instead of integral of 2 pi y. And then that arc length element ds can be written as root 1 plus f prime of y squared, or down here root 1 plus f prime of x squared dx if that's easier. So, and our x we can write as a function of y for the y integral, or just leave it as x for the x integral. And remember what we're doing here. We are integrating 2 pi r and then L for our arc length there. And that was the area of a frustrum. So we're adding up the areas of frustrums. So let's look at an example here. We want to take the curve x equal 1/2 y cubed from 0, 0 to 4, 2. We're rotating around the y-axis here. We're going to set up the integral for the area with respect to y and with respect to x, and then we'll compute the exact area using whichever integral is easier. So let's look at our graph here. I've got this graph that's x equal 1/2 y cubed. So that is our x, which is f of y is 1/2 y cubed. And we're revolving around the y-axis here. So this goes from 0, 0 to the point 4, 2. So it's this piece right here that we want to revolve around. So when we revolve, that's going to hit at -4, 2 right there. And so that's going to look something like this. And when we revolve that around, we get another one of these kind of caved in funnels. So that's what our surface of revolution looks like there. And then notice here at any y value that the radius right here, your radius is going to be the x value. This is a horizontal segment, that's x. So it's the x that's associated with that y value. So that's why we're integrating 2 pi x here, is because your radius from revolving is given by the x coordinate. So let's go ahead and set these integrals up. So in part A, we're integrating with respect to y. So that's the first formula. I went ahead and brought that down here. So we're integrating with respect to y, so we're going to use 0 and 2 as our limits of integration. So this will be integral 0 to 2, 2 pi, and then our function of y, f of y is 1/2 y cubed. And then square root 1 plus f prime of y squared. So if f of y is 1/2 y cubed, then f prime of y is going to be 3 times 1/2 is 3 halves. Decrease your exponent, y squared. And so that's our f prime of y, so 3 halves y squared. And that gets squared. And then dy. So that's the setup for part A. Notice our 2's cancel here, so that makes it a little bit nicer. What about part B? So here we're integrating with respect to x, so a and b are going to be x values. So this is going to be integral, and we're going to use the 0 and the 4. So integral 0 to 4, 2 pi x. And our x is the 1/2 y cubed, but we're just leaving it as x. And now square root 1 plus f prime of x squared. So f prime of x, that's y prime. So we have to solve this original equation for y and then find y prime. So if x is 1/2 y cubed, then multiply both sides by 2. 2x is y cubed. And then take cube roots to solve for y. So cube root of y cubed is just y equals cube root of 2x. But let's write that as 2x to the 1/3 power because we need to take a derivative. So then our y prime, this is a function to a power, so 1/3 comes down in front, times our function 2x, subtract 1 from the exponent, so negative 2/3 power, and then times derivative of the inside, 2. So that's going to be 2 times 1/3, 2/3 out in front, so 1 plus 2/3, and then we've got 2x to the negative 2/3 power. That's our y prime, and that gets squared. Dx. So this is going to involve fractional exponents underneath the square root. I don't like that. So when we're attacking part C to compute our exact area, I want to use this one here. We would get the same answer both ways, but you want to pick the easier integral for sure. So C, our surface area then, is going to be integral 0 to 2. I'm just bringing this integral down. Let's go ahead and factor that constant pi out in front. So pi times the integral from 0 to 2. We have a y cubed left here. And then square root 1 plus. Square the 3/2, we get 9/4. Square the y squared, we get y to the 4th. And dy. And check it out here, y to the 4th and y cubed. So that's all set up for a u substitution here. Let's let u equal 1 plus 9/4 y to the 4th. Then your du will be derivative 1 is 0. 4 times 9/4 is 9 y cubed, and then dy. So we've got y cubed dy, so let's multiply by 9 on the inside and compensate by dividing by 9 on the outside. So we will have pi over 9 and integral 9y cubed dy, so these two here make up your du. And then this is u on the inside of the square root, so root u. And then we have to change our limits of integration over, so if you take y equals 0 and plug it in here, 1 plus 9/4 times 0, that's just 1. Take 2 and plug it in here. So 2 to the 4th is 16. Let's go ahead and work that one out. So y equals 2. Then your u is going to be 1 plus 9/4 times 2 to the 4th here is 16. So the 4 will cancel into 16 and leave us 4. So 4 times 9, 36 plus 1, 37. And then that square root of u is just y to the 1/2 power, or u to the 1/2, excuse me. So this will be pi over 9, integral 1 to 37 of u to the 1/2 power du. That's not bad. So we got a pi over 9 out in front. And now antiderivative here will be u to the 3/2 power, add 1 to the exponent. Divide by 3/2 is the same as multiplying by 2/3. And we're going to evaluate from 1 to 37. And then the 2/3 here, we can factor that out of the evaluation, distributive property. So 2 pi over 27 out in front. And then we're just evaluating in u to the 3/2. So 37 in there, so 37 to the 3/2. Minus, plug a 1 in, 1 to any power is 1. And there we have an exact answer. So that is our exact arc length. So that wasn't too bad. So if you do one of the integrals, x or y, and it turns out to be really difficult, like this one with fractional exponents under the root, Try the other one.